Math isn't all in our heads. You can take any math and apply it to the real world and see results. Some more intuitively than others, like geometry, for example. But let's do that with state space linear systems that we talked about in the last video using block diagrams. We talked about state space linear systems in modern control theory in the last video. I'll put it up right here and you can go check it out and then come back. A block diagram for a linear system is easy. Remember from the last video that U is our input vector and Y is our output vector. Well, this on its own is called a memoryless system. For example, when you use a ruler to measure the height of something and find it to be 5 inches, the ruler doesn't remember that yesterday you measured something else that was 10 inches. But let's say our system had a state that had memory, like position or velocity. Like a car, because it remembered that you parked it and that it was going 10 miles per hour before you found the parking spot. That would fit in between the input and output, the same black box we mentioned in the other video. This block is called our system. We usually use capital P to represent it. There's lots of different types of blocks that you can use. Some of them are familiar from your calculus class, but the blocks themselves aren't that important to us yet. Let's first define 3 very important configurations of inputs, outputs, and blocks. These interconnections are standard. More complex systems are formed from combining these or similar interconnections. There's parallel interconnections, cascade interconnections, and negative feedback interconnections. Let's consider the following general case of 2 interconnected systems. P1, as you can see, it's got its state equation and its output equation, and so does P2. When finding the state space for an interconnection, we use this general procedure. First, we write the complete state equation and output equation using matrices. Then we try to isolate the stacked tall vector x such that it looked like this. I'll solve the parallel interconnection for you, but you'll have to do the rest as homework. First, let's take a look at it. As you can see, the first input isn't changed before going into either systems, so U equals both U1 and U2. But the final output is the combination of both systems' outputs, so Y equals Y1 plus Y2. Now that we're set up, let's write the state equation. Each system has its own state equation. By the matrix addition property, we can split it up. Also, we know we can just use U for U1 and U2. And by block matrix multiplication and scalar multiplication over a vector, we get this. Next, let's do that with the output equation. Each system has its own output equation. Here, we can rearrange our terms. And again, we know we can just use U for U1 and U2. By definition of matrix vector multiplication and the distributive property, we get this. And there you go. Now you know how to derive the parallel interconnection equations. It is very useful to represent a complex system as an interconnection of simple blocks. We call that system decomposition. Here's an exercise problem. Consider a system, P2, that maps each input, U, to the solutions Y of the following equations. We're then told to represent the system in terms of block diagrams consisting of only these types. First, we'll begin by deriving our equations. The state equation can be turned into this, which simply gives us these equations. And the output equation can be turned into this. Now that we're done finding these 3 equations, we can go to Simulink. I am so sorry about the bad quality microphone coming up. This right here is Simulink. And if you haven't heard of it, it's a great tool for simulation modeling using MATLAB. And those are both done by MathWorks, so highly recommend it. And if you are a student, most colleges give their students access to this. But let's try it out now. Let's model using these blocks. I like to work backwards you know, we have a really nice equation. Let's move our input out of the way for now. We have a really nice equation for the output, which is a sum of elements. We can start with that. Sum of elements of one element being 2 times x1 and the other element being 4 times x2. So we have those signals going into our sum of elements and then popping out of the output. And so we know that 4 times x2 is actually x2 with a gain of 4. So let's give it that gain of 4. And that means that this gain received a signal of x2. And similarly with 2 times x1, we have a gain at the tip of that, which received a signal of x1 to become 2 times x1. And we also know that x1 actually comes from an integration of x1 dot, and so does x2 comes from an integration of x2 dot. And we're getting closer to our u here, but I think our job with our output is done, thankfully. So that equation is done. We can move on to the x1 equation. So let's do the x1 dot state equation. And we know that to be a sum of elements also, like our output, which receives a signal of 2 times x1 and another signal of 3 times u. So we're once again getting closer to our input. And so let's start with our 3 times u. We know that to be just a gain of 3 to our signal u, and we've made it. So we connect our input to this gain, which comes into this sum of elements. Now the other element here is going to have to be a gain of 2 to our signal of x1. And we can connect that back around to our x1. So then that finishes it off really nicely, connects the x1 dot to a equation of 3 times u plus 2 times x1. So we're done with our first state equation. Now the second state equation, the x2 dot, is also a sum of elements, a sum of 3 elements. The first one being a negative gain from x2, or pardon me, x1. So negative 2 times x1. There we go. And we can connect that back around to our x1. And the second element is 1 times x2. So that's just this very simple connection back around to this x2. We don't need to add a gain. You could if you want to, which would actually have some benefits, but for our sake, we're just going to leave it like this. But this is just saying 1 times x2. And finally, the last element over here. Oh, sorry, I don't know what's going on. Let me move this line back around here so it looks nicer. But at the tip of this one has to be the third element is 2 times u. So here's a gain. That's 2 times u of u. So we can connect this gain back around to our initial input, and this is our model. So just to show you what's happening here is that we have a signal u being multiplied by 3 times to go into this branch, and then being multiplied by 2, a gain of 2, to go into this branch. And this sum of elements gives us the x1 dot equation, our first state equation. And this sum of elements gives us our second state equation. And finally, they all add up to give us our output equation. So if you follow the signals, you will see how that connects to those three equations. Thanks for watching SciPK. I'm PK, and I'd appreciate it if you like and comment on this video if you liked it. I'd also appreciate it if you could join me on this journey to grow my channel and make cool things for you guys, so please subscribe. And as always, stay curious.